Hello. In this video, we're going to continue studying identities. And in particular, I want us to start with something that seems simple, sine of 15 degrees. Now, I say with a calculator because, well, we know that sine of 0 degrees is 0. Sine of 30 degrees is 1/2. But sine of 15 isn't a unit circle value, so it's not like you could just get it from the unit circle. So go ahead on your calculator, type it in, and if you have just a silly calculator, it'll have something like 0.2588819 and so on, but that's not as nice. If you have the Mr. Peters approved calculator, you should get root 6 minus root 2 over 4. Now, what's interesting about this is an exact value. It seems kind of like a unit circle value. I mean, if you look, there's like a root 2. That kind of reminds you of like a root 2 over 2. I mean, the root 6, that's kind of weird. And the fact that it's over 4. So it's not totally like a unit circle, but I mean, it seems exact. It seems precise. If you type in sine of 14 on your calculator, even the Mr. Peters approved calculator will still give you just a random decimal. Or sine of 16 will be 0.275. Those don't seem special, but sine of 15 seems special. It seems like a special value here. And the question is how? How does this happen? How do we have this special value? And even more so, would there be a way to do it without a calculator? Would there be a way to do it without a calculator? Because if it's an exact value, and if it's somehow related to the unit circle, you would think you could get there without using a calculator, but how? Now, one thing I want us to think about is if we were to go to the next one, sine of 45. Sine of 45 is root 2 over 2. And I want you to think about those angles 30 and 45. 30, 45, how much more is 45 than 30? Well, 15 degrees. So there seems to be some relationship here where it's kind of like you're going up 15 degrees on the unit circle. So maybe that's why sine 15 has this special value. But that's not going to be quite enough to get us there. So the second hint would be to look at your formula sheet. And if you take a look, you might see something with a sine and an alpha plus beta or alpha minus beta, maybe something like that. Alpha and beta, just so you know, alpha is just the letter A and beta is just the letter B, but these are in Greek and these are in English. Sometimes in math, we use other letters, right? A theta is a Greek letter. You might have seen letters like lambda in physics, or maybe a cool letter like a psi or a phi. These are all just Greek letters, and we use them because sometimes we run out of English letters to represent all our symbols, so we use Greek ones. All right, back to the formula sheet. If you look at sine of alpha minus beta, the formula sheet says it's sine alpha cos beta minus cos alpha sine beta. So in other words, if I have two angles and they're being subtracted, the formula sheet says that that's the same as doing sine of the first angle, cos of the second angle, minus cos of the first angle, sine of the second angle. Okay, well, how could we combine these two? And I'd encourage you to pause the video now and see if you can play around with this. Use the angles 45 and 30, plug them into the formula and see what you get. All right, so hopefully you gave it a try and you wrote it like this. Alpha will be 45 and beta will be 30. So we have sine of 45 minus 30. And according to the formula, that will be sine 45 cos 30 minus cos alpha, so cos 45 sine 30. Now the nice thing about this is on the left-hand side, if I were to simplify this, 45 minus 30 in the brackets is 15. So the left-hand side of this formula represents sine of 15, the question that I'm trying to work on. And the right side represents a bunch of unit circle values. Sine of 45 is root 2 over 2. Cos of 30 is root 3 over 2. Cos of 45 is root 2 over 2. Cos of 30 is 1/2. Or sorry, sine of 30 is 1/2. Now root 2 times root 3 is root 6. 2 times 2 is 4. Root 2 times 1 is root 2. 2 times 2 is 4. Common denominator, root 6 minus root 2 over 4. And hey, we have the same value as our calculator. And we didn't need to use our calculator. So what is sine of 15? Sine of 15 is root 6 minus root 2 divided by 4. And we can determine it by using our formula sheet with this special formula, and of course with our regular unit circle values. Now, this idea opens up a whole realm of new possible angles. For example, sine 75. If you think about the number 75, it's not on the unit circle, but you could make it with unit circle values. 75 is like 30 plus 45. And if you take a look at the formula sheet, there is a formula for sine of one angle, alpha, plus sine of another angle. So sine of alpha plus beta is equal to sine alpha cos beta plus cos alpha sine beta. So go ahead and pause the video, plug in those angles, and see what you come up with. All right, so assuming you gave it a try, we should have here, let me see if I can do this in another color. Let's do the angles here in blue and green. So we have sine of 30. Then we have cos 45. Right, this is my alpha, this is my beta, plus cos 30 sine 45. Now it's just unit circle time. This is going to be 1/2 root 2 over 2, root 3 over 2, root 2 over 2, so root 2 over 4, plus root 6 over 4, so root 2 plus root 6 over 4. And if you want, you can double check on your calculator. Sine of 75 is indeed root 6 plus root 2 over 4. You could write them in either order because it's addition, so it doesn't matter. All right, could we do the same trick in radians? Could we find cos of 5 pi over 12? Well, if you notice, 5 pi over 12 isn't one of the unit circle values, but the question is, could you make it with unit circle values? And the fact that we're using cos here, don't let that alarm you. It's the same as with sine. If you look on your formula sheet, there's a formula for cos of alpha plus beta or alpha minus beta. You just follow along with the proper formula. So go ahead and pause the video and see if you can work out the exact value. All right, so assuming you gave it a try here, we could take 5 pi over 12 and we need to split that up. Now you could split that as maybe 2 pi over 12 plus 3 pi over 12 because 2 plus 3 is 5. So this would be pi over 6. This would be pi over 4. And if you notice, those are both indeed unit circle values. Let me do them maybe in another color here, just so we've got them nice for our formula. We'll do this one in blue, pi over 6. Do this one in green, pi over 4. Now the formula is cos alpha plus beta equals cos alpha, cos beta, minus sine alpha, sine beta. And you just follow along with whatever the formula sheet says. So here we'd have cos pi over 6 plus pi over 4 equals, so it's cos minus sine, kind of a interesting formula here. Alpha goes here and here. Beta goes here and here. Now cos of pi over 6, remember that's 30 degrees, so that's going to be root 3 over 2. This one's going to be root 2 over 2. This will be 1/2 root 2 over 2. And so we have root 6 over 4 minus root 2 over 4, which is root 6 minus root 2 all over 4. Now, just one thing to keep in mind on this question. If you had a difficult time splitting up the 5 pi over 12 into two unit circle values, you could do this question in degrees. I mean, I like to do things in radians, but if you were just totally struggling and you couldn't come up with two unit circle values, you could take the 5 pi over 12. Remember, we can multiply by 180 and divide by pi to convert it into degrees. So this will be 5 times 180 over 12. Now 180 divided by 12, again, we don't have a calculator, but I guess we could divide, well, the 12 is even, so we could make that a 6 and then a 90. Then we could divide again, that'll be a 45 and that'll be a 3. And 3 goes into 45 15 times. So 5 times 15, that'll be 75. So we could convert it into degrees, and obviously once you see the 75, you're like, oh yeah, that's 30 degrees plus 45 degrees. So if you want, that's another way of solving this. Again, I don't really recommend it because I like to think in radians, but if you get really stuck, you could convert into degrees. All right, so here's another one. We have cos of 17 pi over 12. I would encourage you to try to find two radian angles that either add up or subtract to get 17 pi over 12. But again, if you are really stuck, you could try going to degrees. All right, so the one that makes most sense to me would be writing this as, instead of 17, I'll split the 17 into a 3 pi over 12 and a 14 pi over 12. Because 17 is 3 plus 14. And 3 over 12 will be pi over 4. 14 over 12 will be 7 pi over 6. And both of those are unit circle values. Since we're adding them, we use the formula that says cos alpha, cos beta, minus sine alpha, sine beta. That's the one for cos of alpha plus beta. I know the cos formula is a bit weird. When you plus between the angles, you minus on the cos formula, and then when you minus between the angles, you add on the cos formula. It's just a little quirk of how the formula works. All right, so let's go ahead and set this up. Cos pi over 4, cos 7 pi over 6, minus sine pi over 4, sine 7 pi over 6. So that's root 2 over 2. Then we need cos of 7 pi over 6. That one's a little tough, but we should come up with negative root 3 over 2. Here we got a root 2 over 2. Then we got sine of 7 pi over 6. It's going to be negative a half. So this is negative root 6 over 4. Minus minus makes a plus, root 2 over 4, for a total of negative 6 plus root 2 over 4. And again, you're welcome to check this answer on your calculator, assuming you have the Mr. Peters approved calculator, and you should get the exact same thing. Now, just for fun, we could also do this with tan. So here's tan of 105, right? 105 is not a unit circle value, But real quick, try to think of two unit circle values that either add or subtract to 105. All right, so two that pop out for me would be 45 and 60. Now the tan formula, ooh, this one's pretty tough. I'll try to write it out nicely here. So tan of alpha plus beta is equal to tan alpha plus tan beta divided by 1 minus tan alpha times tan beta. So the tan formula is not a fun one because there's division and a lot of stuff going on there. Maybe just let me clean up the top a little bit there. Tan alpha plus tan beta. So there's a plus, there's a minus, there's a times, there's a divide, there's all the stuff. But once you have it written out, you should be able to rock and roll. Let's go ahead and see. We've got this as our alpha, this as our beta. So that means we should have tan 45 plus tan 60 divided by 1 minus tan and tan. One of them gets a 45, one of them gets a 60. All right, now, so this is what tan of 105 equals. Now we got to do each one of those. Remember the tan unit circle is a little tough. 45 is easy because that's where sine and cos are the same, so that's just 1. So that's 1, that's another 1. Tan of 60, that's going to be just root 3. So now we have plus root 3 times root 3. So this is 1 plus root 3 over 1 minus root 3. Now, unfortunately, if you type in tan of 105 on your calculator, it's not going to give you something that looks like this. It's going to give you something that looks like this on your calculator. -2 minus root 3, which looks totally different. Now, just so you know, this is correct. And actually, if you try to type this in on your calculator and then hit equals, it will actually simplify it to this, because these are actually the same thing. Again, right here, you can stop. This is full marks. You haven't simplified enough. But for fun, I want to show you how your calculator takes it from one to the other. Remember that skill of rationalizing. We multiply by 1 plus root 3. 1 plus root 3. And so because the denominator has a root in it, we multiply by the conjugate. We flip the sign from negative to positive. Do that on the top and the bottom. The top is going to FOIL out to 1 plus root 3 plus root 3 plus 3. The bottom FOILs out to 1 plus root 3 minus root 3 minus 3. These middle terms always cancel when you do this. Then you get 4 plus 2 root 3 over 1 minus 3 is -2. Now we can take that -2 and divide it into both of the terms. So 4 divided by -2 is -2. 2 divided by -2 is -1. And there we have it, the nice simplified version. So again, you're welcome to leave it at that original one, right? This is good to go. But it's nice to see how your calculator takes it all the way. And if you're comparing your answer on a question somewhere, depending on how the computer generated the answer, it might be rationalized all the way. So this is a helpful skill just for comparing your answer. If it looks different, it might not actually be different. All right, a few last problems to work on here. This is sine 5 pi over 18, cos 7 pi over 18, cos 5 pi over 18. What in the world? I don't think I know any of these numbers. Sine of 5 pi over 18 isn't something that I know, and 7 pi over 18, these don't seem like unit circle values. Go ahead and pause this video and see if you can try the problem. All right, I really like this one. I think it's clever. This is kind of like my alpha, and this is my beta, right? You can see again we have alpha and we have beta. And so this whole thing, this looks like the right-hand side. This looks like the right-hand side of an identity. It looks like someone's already expanded it. So can we put it equal to the left-hand side, the original one? The original one would have been sine of alpha, because you notice it goes alpha, beta, so that tells us it's the sine one, right? Sine, cos, cosine. That formula looks like the sine of alpha. We got a plus there, so I think sine of alpha plus beta. And so if alpha is 5 pi over 12, we could write this as 5 pi over 12 plus 5 pi over 18 plus 7 pi over 18. And then we could actually add those two. We have a common denominator, so that'll be 5 plus 7, which is 12 pi over 18. 12 over 18. Oh, we could simplify that. Divide them both by 6. So 2 over 3. Oh, and well, sine of 2 pi over 3, that's a unit circle value. That's something I know. Sine of 2 pi over 3 is equal to root 3 over 2. Now, if you wanted to check your answer a different way, you could type this whole monstrosity in on your calculator, and you would indeed get root 3 over 2. It's sort of like someone tried to use the formula, but when they split up the alpha and beta, they picked terrible alpha and betas because they're not numbers that we know, not unit circle values. So the way you solve this problem is instead of using the expanded version, this is kind of like the expanded version, what you do is you go backwards and you compress it. You go back to the compressed, the one where the alpha and beta are together inside the brackets, and then it actually works out pretty nicely. Now we'll go ahead and take some notes on this here. And the basic concept for what we were working on is they're called trig identities, addition, and subtraction. Addition and subtraction. Now, the really important thing with what we are doing, and I didn't want to talk about it to the very end, is that we can't do this, okay? If someone asked you to find sine of 75 degrees, you might be tempted to say, well, that's the same as sine of 30 plus sine of 45. I've been paying attention, Mr. Peters. I know 75 is not a unit circle value. 30 and 45 are. I'll put it as plus. Then I know that I'm allowed to just distribute things, just FOIL it in. Sine 30, sine 45. Sine of 30 is a half. Sine 45 is root 2 over 2. So I get 1 plus root 2 over 2. Box the answer, and we're good to go. But if we check on our calculator, sine of 75, according to our calculator, we have root 6 plus root 2 over 4. Now, again, you might be tempted, oh, maybe these just look a little different. But as a decimal, this is 0.966. The other one is, let me just type it in here, 1.207. These are not equal. These are not the same thing. And the reason why is this step right here. This step where we took the sine and we FOILed it out is not legit. This is not allowed. We didn't do it all lesson, but I have to do it now because I know someone's they're just gonna try it, trying to be fancy. You can't do this. This is illegal. You only can do one thing. If you see sine of an angle plus another angle, well, you might be tempted to just say, hey, let me just sine them both and put a plus and call it a day. You're not allowed to. It doesn't work. I wish it worked. I truly wish that this gave us the correct answer because, I mean, this would be so much quicker. But it doesn't work. And if it doesn't work, we can't do it, as nice as it might be. Instead, we have to do sine of 30, and then we have to stick a cos of 45 on it. Then we can put a plus, but then the next term is going to be a cos of 30, and then a sine of 45. This is the proper move. Here, this is legal. Unfortunately, though, like we said, this over here is illegal. The legal stuff is right here. The rule is that if you're going to have two angles and you have a sine out front, you can't use some kind of weird shortcut. You have to use the formula. It's longer, I get it, but it's the only way to get the correct answer. So for a problem over here, why don't you guys try this? I'll give you one of those silly ones. Cos 2 pi over 9, cos pi over 9, minus sine 2 pi over 9, sine pi over 9. My advice to you would be to compress it and then find the value. All right, so hopefully you gave that a try. This looks like alpha, beta, alpha, and beta. And because we have cos, cos, and then sine, sine, this looks like cos of alpha. That negative sign makes it a plus, so cos of alpha plus beta. In other words, we could compress this to be cos of 2 pi over 9 plus pi over 9, which would be cos of 3 pi over 9, which would just be cos of pi over 3, which is 1/2. And that would be our final answer. Now for your notes, this is Unit 7, Worksheet 4, so you can try one of those. And then any things to remember over here. Again, one thing might be that if you have an angle like 105, right, you got to write this as maybe like a 60 and a 45. And the same thing if you have it in rad, you have to do the same thing. Now before we end, I just want to show a couple more things. So if you're interested, and you're wondering where do these identities come from, they don't just come from the formula sheet, there are some proofs for it. And so I'm going to link to another YouTube video in the description, and I'd encourage you to go ahead and click on that video if you want a nice in-depth proof of how these identities come about. If you're just fine to take the formula on faith, that works too, but it is nice to see a geometric proof of it. So I'd encourage you to check out that video in the description. And one last thing, I want to show you an extra super problem. So here we have this triangle, and we're asked to find cos of angle ABC plus 60 degrees and try to figure out what it is. This is just a really nice problem. It's kind of weird. There's a triangle, there's a cos, so what's going on here? I encourage you to pause the video and try to work on this a little bit. It's just a really neat application of this formula. All right, so assuming you paused it and gave it a try, cos of angle ABC means we go A, B, C. So we can put a little alpha in there. That's the angle we're looking for. Well, actually, we're not looking for the angle. We're looking for cos of that angle plus 60. Okay, well, we know the formula is cos alpha, cos beta. Oh, but beta is 60, so we could put cos 60 minus sine alpha sine 60. Okay, well, we know cos of 60. Cos of 60 is 1/2. Sine of 60 is root 3 over 2. But what in the world is cos of alpha? Well, think back to SOHCAHTOA. Because we have a triangle in front of us, we can figure out cos of alpha. Cos is a ratio, and cos of whatever your ratio is, or your angle I should say, is going to be the ratio A over H. Based on the triangle, This is your adjacent. And this is your hypotenuse. So cos of alpha is 15 over 17. Similarly, sine of alpha is opposite over hypotenuse. This is your opposite, the 8. Hypotenuse is 17. So 8 over 17. So we can plug both of these values in as 15 over 17, 8 over 17, put the minus sign, and that gives us 15 minus 8 root 3 over 34. Not the nicest number you've ever seen, but kind of fun, able to solve this sort of intricate puzzle using our SOHCAHTOA and using our new cos formula and just working it all out to get this nice final answer. All right, hopefully you enjoyed that video, and as always, thanks for watching.